everyone, and welcome to the second day of Understanding Deep Learning, an event offered by Data, uh, a student group on data science and machine learning. Our intentions with this event is to promote knowledge in an area which is often mystified by inviting professors and researchers from all around the world to talk about their discoveries in this area. Before introducing our speaker, I would like to thank University of São Paulo and the Institute of Mathematics and Computer Sciences for their help in advertising this event, and especially neural networks, abstract relational reasoning. Our guest is Bruno Ribeiro, who is an associate professor in the Department of Computer Science at Purdue University and a visiting associate professor at Stanford University from 2023 and 2024. Before joining Purdue, he earned his bachelor's and master's degree from the Federal University of Rio de Janeiro and his PhD from the University of Massachusetts Amherst. He was also a postdoctoral fellow at Carnegie Mellon University. He has made significant contributions in the intersection between geometric deep learning, graph neural networks, out-of-distribution robustness, and machine learning. He has received several awards, including an NSF Career Award in 2020 for his work on the foundations of graph machine learning, and an Amazon Research Award in 2022, and multiple Best Papers Awards. Before we begin, I'd like to give a brief message to the Portuguese speakers. Boa tarde. Essa palestra vai ser totalmente ministrada em inglês, mas já no período da tarde, se vocês tiverem alguma dificuldade em entender ou preferirem realmente assistir com as legendas, já vai estar disponível aqui no canal do Data. Feel free to ask any questions during the talk. We will have questions and answers section at the end of Bruno's talk. Now, Bruno, shall we begin?
Yes, I'm ready. Thank you, Mariana, for the kind introduction, and thanks for the organizer to invite me. It's a great pleasure to be here. I've been to USP many times, and I really enjoy whenever I visit. Falar em português, obrigado por me receber. É sempre um grande prazer falar com os alunos da USP. Today we're going to talk about the foundations of cross-domain transferability in neural networks. I hope you can see my slides fine. So the standard notion of robustness in machine learning, you have some...
Bruno, just a minute. Can you share it again, please?
Oh, is it not working?
Yes.
Oh, okay. I guess it stopped working then. Okay. We are fine. Can you see me? Can you see now?
Yes, now we can see.
Okay, good. Hi, so I'll talk about foundations of cross-domain transferability in neural networks. So the notion of standard ML robustness is really that you have some training domain here on the left, right? And represented by these dots with different colors, which could be different labels. And then the test domain is different than the training data, but not different domain. It's the same domain. So if you are talking about customers on Amazon, and the test domain is also customers on Amazon. And then interesting tasks in these domains would be to reduce generalization error, right? And overfitting, adversarial robustness, et cetera, et cetera. So these are really important tasks to have, but there is one issue generally in deployment is that when you deploy your machine learning model, the data that you use for training is likely different than the data that you use for test, right? And one way to solve this problem, which is the most common way, is with data augmentation, right? So you go and you try to make your data look more, your training data look more like the test data that you have. For instance, for convolutional neural networks, you have, say, this cat here is original image, and then you essentially transform the cat by rotating, clipping, and scaling the cat so that your neural network, when it sees, say, a close-up of a cat and the light is slanted, it's not going to get confused and also identify that as a cat. The same thing, for instance, for Tesla, their self-driving, they have this, they simulate people running on a highway because they don't have training data like that. And to make sure that the cars are safe, you have to simulate and show examples. That's known as data augmentation. So essentially transforming your training data to look more like the test data. Well, but there is another challenge, is that not always we can do that. Either because we don't know the transformations that are necessary, or because we have no idea what the test domain looks like at the moment, right? So the task then for zero-shot domain generalization is that you have some training domain here, and the test domain has some differences between the training domain that you don't know ahead of time, and now you want to learn a model in training and apply in test in a way that's robust to these potential changes. So the zero-shot domain generalization then is that the predictors directly apply to the test domain. It's unlike other approaches like dealing with data distribution shifts, in that you're really just pre-training the model and directly applying to the test domain. You're never seeing this data. So the main challenge then is that the training data alone does not disambiguate all possible hypotheses for the predictor, right? So if you don't know what the test domain looks like, then how do you know what kind of things in the training domain, rules that you can learn that could be applied to the test, right? And the idea that, say, Occam's razor can help solve this issue, right, that I don't believe. Because the notion that having just smaller models, the same way that we used to do with generalization error, right, it's just not enough, right? Because it's unclear that first it's unclear what simple is for a neural network, and then also the robust rules that transfer between these domains may not be simple rules. They may be a bit more complex. So we have done a bunch of works on this kind of auto-distribution generalization, and more recently been quite focused on zero-shot domain generalization. And here are some of the works that are related to this. I'm going to give you three different tasks domain for zero-shot domain transfer, and we are going to go over those right now. So the first one is, so why would be interested in that? Say that you have some knowledge base on sports, right? And you have some, say, this graph which represents like sports relationships, right? This knowledge graph. And then you want to train on sports, and then essentially with the trained model, pre-trained model on sports, you want to directly apply to predicting things on this knowledge graph on organizations, right? So the task could be, for instance, predicting that there is this missing link here in both domains, but you are only training on sports and you want to directly apply to organizations. So this change in domain means new entities and new relations, right? And no zero-shot really means there is no retraining, no semantic information, no side information. The model is just going to get the input data and make a prediction. Another case, for instance, is, for instance, you have this recommender system that is predicting which customers are purchasing which products. And suppose that you have trained this model on a phone store, right? It sells phones. And the phones have price, have a amount of RAM, have a battery, the amount of battery that they have. And then the customers can view or purchase things on this store. And then what you want to do is you want to predict for customer V whether it will want, given it saw product J, if it wants to purchase this other product here. Right, so this is a task that's very important in e-commerce. And the challenge is that suppose that you train on the phone store and now you use this model directly on clothes, right? So clothes have different, very different attributes, right? So the features in clothes would be, say, size, color, fabric, and suppose that we cannot see the price, right? A lot of the data sets in this that are available don't really have prices of the clothes. So you want to be able to predict this. You could have the price, but assume that you don't. So there are really no overlap between the features on the phone store and the features in the clothes, right? They're very different. But you want to be able to zero shot, meaning you pre-train on this training data, and then you directly apply on the test data without having to retrain the model. So what's important here is that not only changes the products, changes the customers, but also changes the feature space of the products. Another example of zero-shot domain generalization is in neuro-algorithmic reasoning. If you think about how algorithms work in real life, this is a bit the way that I like to think about it. So if you think of an elephant, right, this very complex object is very difficult to model and find solutions because the problem is actually very complex. That's the real data. And then we generally, to build algorithms, we simplify the data, right? So the data, we imagine the data to be a much simpler problem. And then we design an algorithm over this simpler problem. So there are many different ways of solving it. I'll show an example with linear programming. And then we design the algorithm for the simpler problem. And then we add a bunch of engineers to just fix the issues because the algorithm is not really good on the original data. It's kind of okay, right? We need to fix the solutions. So we have hundreds of software engineers to add, say, if conditions to the algorithm, right, to fix it so that the solutions are improved. So there are a bunch of heuristics usually on top of this kind of simplified algorithms. And what we would like to do is not to do that, right? We would like to run the algorithm directly on the real problem, on the real data. And that's where neural networks can help. So I'll give you an example, for instance, that we have worked on. So we have some routing traffic on the internet or data centers. So you have this demand between the different points of the internet. So we want to send traffic from Stanford to UCSD, for instance. And then there are many routes that you can take. These are called tunnels to take the traffic. And then at Stanford, we need to decide how to split between the red and the blue tunnels, right? How much traffic goes on each. And this is what happens in data centers and internet everywhere, right? When you send traffic, you need to decide how to split through the tunnels over. So the challenge with this is that if you try to, this problem seems like just a linear programming problem, right? You have some constraints and you have to route traffic in the optimal way according to some optimality metric. So that seems like a simple problem, but the reality is that we don't really have the data because the input data that we are deciding our splits is the present data, not the future data. And the future data, we don't know. What happens is that the demand may change, and there are these black swan events. Sometimes there is some big change in demand in traffic on the internet, and you need to make solutions that are robust to these changes. The challenge is that you really can't really predict the changes very well. So it's hard for traditional optimization methods to deal with this, on top of the fact that there are many other simplifications that are done to be able to use something like linear programming in order to solve this problem. So that's one part where neural algorithmic reasoning can help, right? And again, the problem is the domain transfer, right? If I train my neural network on the US, and now the US topology has changed suddenly, right? There is a hurricane, and now Florida routers are not working. Then how would the neural algorithm deal with this sudden change in the topology, right? These sudden changes, and that's essentially a change in domain, which is hard to deal with. So the important thing is that for something as important as routing, you want to make sure that even if you're given garbage predictions on the demand, right, your demand predictions are pretty bad, you still have decent outputs, right, so that your traffic splits are still good, even if your predictions for the demands are not that great. And the third case is a case that we have been working recently, where the thing about real science discovery is that it's generally out of domain. What I mean by that is, suppose that we want to simulate flow on this wing, right? So we have the wing. You can imagine this as the wing of an airplane, and this is the speed of the air, and then this is measuring the speed of the air after it hits the wing, right? So you can see that there are lower pressure points and lower speed points in the when the fluid interacts with the wing. Then the idea of using neural networks here, for instance, is that you can have much faster solutions, right? So the simulations are pretty slow. They take many weeks in the supercomputer, and you want them to be a lot faster, and using neural networks to make them faster. The challenge is that, as we'll see, the methods that exist, they essentially all fail in new domains. So if you have trained on some set of conditions, and then you apply your pre-trained model, right, in a different set of conditions, they tend to give nonsensical answers. And that's the problem, because really, like, you want to be able to do the simulations in order to design better airplanes, right? Design better vehicles, and designing something new means it's not in this, like, your training data, right? And that oftentimes becomes an out of domain question, or you can say out of distribution, but in some cases it's even out of domain, depending on the speed of the flow. So I'll give an example for physics, the very simple one. Think of about an ODE where we have this pendulum, and this is this rod is a fixed rod, right? It's rigid, and then suppose that we have trained this rod in where the pendulum was oscillating in very small angles. And now we want to test the neural model where the angle is much larger, right? So when we do this, the existing physics machine learning methods just fail, because this is a completely new environment, which we call it an auto distribution environment. And in auto distribution environments, this neural models generally have significant issues. So, for instance, if you do that with some of the state of the art, then we'll see that, you know, if your test domain is similar, like it's the angles are pretty small, generally most of the methods work well. So here we are given the past and ask the model to predict the future, and you can see that if you intervene and you, in your test data, you push the pendulum way up, something that was never seen in training, you can see that the existing models are just output nonsensical answers, right? Because they never seen it, so the neural network gets confused. So, and you can say, well, you know, this question seems really hard, right? So, but humans seem to do pretty well, right? How do we do zero-shot transferability across domains? And I'm making a quick detour here to explain a concept of symmetries. So the symmetry of an object X is a mapping of the space of X onto itself, which leaves the object the same. So here we have this snowflake has rotation and mirror symmetries. A butterfly would have mirror symmetry. So if you put a mirror, you see the same butterfly. And this starfish has some rotation symmetries, right? So nature has some symmetries in it, and the notion of symmetry is just that if you apply some transformation to the object, The object remains the same. So what about humans then? During COVID, I was teaching my son to math, and it was quite interesting because at that age, he had this persistent mistake of mixing up 6 and 9s, right? He would see a 9 and would say 6. And I found that quite interesting because it was consistent. And then once he started going back to school, one of the first homeworks that his class got was really this one, right? Where they had to identify P, B's, Q, and D's, and also 6 and 9s. So they have to identify them to make sure that the children understood that these are different things, right? As an adult, you see they're pretty different. But the thing is that children can't, right? They have these symmetries in their minds, and you have to teach them to identify the differences, that these things are not the same thing. And it's interesting if you think about how neural networks work, which is very different, right? Because a neural network, like any simple CNN, has no problem in distinguishing 6 and 9s because they are not rotation symmetric, right? A 6 is can be seen as a rotated 9, but the CNN doesn't have that kind of invariance, right, to rotations. So it can easily identify those two 6 and 9s. And same thing with P's and B's and D's. And then when I looked at this, I got very interested in this, and I started studying this. And one of the things that I found out is that assuming symmetries is a key cognitive difference between young children and other primates. So if you get a young child and a primate and you give them tasks that they both can do, right? The child will assume a symmetry, like the human child will assume a symmetry, while the primate will not. So I'll give you an example. So if you give a stimulus E and then D, and then if the child does Z, gets a reward, right? And the ape does Z, gets a reward. Then the child immediately assumes that no matter which order, if you're given E and then Z, they have to do D. If you do D, then E, they have to do Z. So they know they have all these symmetries. They imagine that the order probably doesn't matter until they are given evidence that it does. And then they learn that in that specific case, the order matters, otherwise it doesn't. And for primates, the order generally always matters. And that's one of the kind of defining characteristics of human intelligence. With that in mind, so one of the things that we started was to look into how to port that concept to neural networks, right? So that neural networks behave a bit more like our brain in that case. And the hypothesis we had is that the human brain assumes symmetries to learn domain transferable rules. And this is really the topic of this talk. So there is this work that we did on asymmetry learning, and a lot of what I'm going to talk about is based on this understanding. And I'm not going to go into details. It's actually I really like this paper. It talks about training neural networks from invariances. It's as invariant as it can be, right? So all possible transformations won't matter. And then the neural network actually learns to not be invariant to something only if it sees evidence that not being invariant to it is useful. For instance, my son had a P and Q, right? He would get it wrong if he assigned P and Q the same label, right? So then he was taught to not have that kind of symmetry between P and Q. So the hypothesis is really that this domain transferability happens through symmetry constraints, the notion that things are the same. And regarding graphs, one interesting thing about the graphs is that graphs, when we say we have a graph, we're essentially saying that we have some symmetry in it. So if you think about getting a graph and making into a string, right? So you have this graph here, and you try to make a string of a sequence of edges, right? Describe the graph as a sequence of edges. So you have a function that maps from the graph into a string, and there is a function that maps from the sequence back to a graph. So when you represent a graph in your computer memory, you represent it as a string, right? It has to be a sequence in your memory. So that's essentially how it's represented in the computer anyways. So then the thing is that, you see, these two graphs, this graph here and this graph here, are isomorphic. The only difference between the graphs is that the IDs of the graphs are kind of arbitrary, right? I'm calling node 1 this one, node 2 this one, node 3 this one. I could just have called 3, 4 and 4, 3, right? I could arbitrarily have called 5, 2 and 2, 5, right? So I could have switched their IDs. And then I would get essentially the same graph. It's just an isomorphic graph. It's just because the IDs don't matter, this graph and this graph are the same input, which means it's a symmetry, right? It's a transformation that maps the object into the same object. So then, but if I were to make this graph into a string, now we can see that this edge here, 1, 3, is different than the edge 1, 3 in this string, right? So the strings are different, but the graphs are the same. And essentially, neural networks that work on graphs, they have to have this property that they would give the same output no matter which of these two graphs I gave. Okay, so these distinct strings are the same graph, therefore the predictions in the graph need to be the same. So one thing, quick thing about sequence models is that sequence models don't have this symmetry, so it's hard for them to predict inputs that have this kind of symmetries, right? So if we have this graph here and you ask a question for a sequence model like a large language model, you have to make it a sequence, right? This graph, describe this graph into a sequence, and if you give different sequences, the model can give different answers. What has been happening lately is that these are now usually fed into some graph type algorithm, and which then doesn't have this issue, right? But if you get some standard LLM, large language model, it will generally give you different answers for different ways to describe the graph. So, but because it doesn't respect the symmetries, right? These are sequence models, and it's normal that it has different embeddings for different orderings. So what if we constrain, say, this graph neural network, this neural network, to even have stronger symmetries than just this permutation symmetry we are talking about? So I'll give you two examples. The first one is on what we call double equivariance. And the idea is that you have this knowledge graph here, right? Entities and relations. And then what you want to be able to is to train on one domain and then be able to predict on a different domain without retraining, right? As I said earlier. So how can we transfer these relational patterns that you learn in one domain to another domain? Essentially, what you do is you say, well, in this graph, I'm going to assume that the types of relations don't really mean anything. They are exchangeable. So I can put any string here to describe this teammate. I could replace with anything. As long as I replace it consistently over the graph, these graphs are the same, okay? So once I do this, then I force my graph neural network, which is this GNN square here, to have the symmetry where it doesn't matter the ordering of the nodes, like which this entity ID is in the memory, it doesn't matter. But also the ID of this relation also doesn't matter. So the neural network should ignore the names of the people and the entities and the names of the relations, okay? It should always ignore them. They are not relevant, but it's not just removing them. It's essentially a notion of symmetry, right? So if you look at these two graphs, you can see that the organization graph is symmetric to this graph if we replace team principal with CEO, replace racing driver with employee, and replacing teammate with coworker. You see, it's the same graph. And then when you learn here, it essentially also learning here, like, because the rules that you are learning are not specific to the type of relation. They are more general, right? They can be applied on this case. While this seems like a very strong assumption, it's actually not. So if you design neural networks this way, what we call double G equivalent neural networks that have this property I described, then if you train on Wikipedia, separating Wikipedia by domain, say art, awards, education, health, infrastructure, location, etc., then when you learn in one domain, if you train this neural network to predict relations in one domain, and then you apply in a not different domain it has never seen, this line here means that it's as good as the model that was trained on that domain. So if my domain is, for instance, organizations, a model trained in organization will have some performance, right, in the organization itself. But then I train on, say, arts, and then I test in organizations. So if the models have the same performance, it's going to be here at 0, okay? The prediction performance is at 0. And you can see that as we give more and more domains to train, in testing a new domain, the model that is trained on more domains get as good, sometimes even better, than the models that were trained on the domain in test. So the ones that were trained on organizations are not as good as the ones that were trained on other domains. And that is consistent. If you look at cross domains and you do this many, many times, you see that there is a consistent, and that's what these bars are. So is a similar thing for predicting. If I give a node and a relation and predict which other entity is related to this one. And it's the same thing we see, right? As you train with more domains, you can now zero shot into a new domain almost as well as if you train on that domain from the beginning. So this is quite interesting. There are a bunch of works after hours on this notion of double equivariant models. So these are all double equivariant models. And they essentially have the same principle, right? That you are training a graph neural network that doesn't care about this relation IDs. It assumes a symmetry between the IDs. Okay, so another case is also interesting case is where we have to transfer between domains where the domain is a feature space, right? So the features of phones are very different than the features of clothes. And then you have to learn something that's able to transfer between these two domains without retraining. And then you can think, oh, I could use a large language model, right? I can give these features to a large language model and get an embedding for these features and use that. And then for this other domain, I embed this and I use that. But you can see that the type of embedding that the large language model is going to give to this is probably quite different than it's going to give to this, right? So your model will be a bit confused, and that's what we actually see is that if the domains are quite different, then using trying to predict what this person is going to purchase in test by training on a different domain. So if we train on all domains except desktop and try to predict what kind of desktop this person is going to buy on a store, an electronic store, using graph neural networks and LLMs for the embeddings, normalization, the structure, remove the features. So none of these perform much better than the other. There are really tiny differences. LLM sometimes beat the others, but by very little, and sometimes it doesn't. So here we are training, for instance, on bad desktop smartphone shoes, and then testing whether we can predict selling refrigerators, right? which have very different feature spaces. So essentially, this problem has been open for a while, and the thing is that what we have shown in our work is that there's if you use invariances to define how embeddings encode dependencies between the features, then the notion of dependencies is transferable across domains. And that means that if I train on other online stores, right, and I test on desktop, I can significantly improve over what we have, like ignoring the features, right? If you ignore the features, everything, LLMs, everything gets similar performance, but with this new approach, with symmetries, you really get a big boost. So imagine now we are training on refrigerators, desktop, beds, smartphones, shoes, and then we apply on clothes, right? And this data set here doesn't have any prices, anything. So you can see the big jump that is by doing this type of transferability. So I'll just go very briefly now over asymmetry constraints for neuro-algorithmic reasoning. I highly recommend, if you're not familiar with the topic, the work of Petar and Charles. It's very interesting work. I think it's super nice. And one of the things that I was being fascinated is that to me, neuro-algorithmic reasoning is one of the frontiers of being able to really have domain transferable algorithm neural networks, because algorithms need to work on all domains. So this work we will show that. Again, the problem is I give you some domain traffic on the internet. These are sources, these are the destinations, and this is the amount of traffic goes between source and destination. And I give you some tunnels in the internet where things go and the topology of the internet, and you have to tell me how percentage of the traffic that goes from one source to a destination, how much will go on each of these paths, right? The method must be robust to changes in topology, capacity, and tunnels. It also must be fast. So the one thing that I would say is if you like hypergraphs and hypergraph neural networks, this is a perfect problem for you, because the tunnels are essentially hyper edges. But the hyper edges have an important property because of the way that traffic routing works, is that whatever is the bottleneck on this, doesn't matter where the bottleneck is on this path, that bottleneck determines how much traffic goes through the entire path, right? And therefore, when we are talking about modeling, how do we describe this path to a neural network, we have to tell the neural network that the order of the edges in the path is irrelevant, right? So essentially, when we model it, we have to model as a set of edges. And that is very tied to the way that the problem works, right? So if you put a bunch of symmetry constraints on your neural network, then that is symmetries for permutations of traffic matrix and adjacency matrix. So essentially, if you go in and you transpose the traffic matrix and your routers are symmetric, then the traffic from Stanford to UCSD should behave the same way between UCSD and Stanford, right? If they exchange traffic now, UCSD is the same, sending the same amount of traffic to Stanford, the routings are supposed to behave the same. So the other thing is that the order in which you give the tunnels to the algorithm should not matter. And then reordering of the edges inside the tunnel should also not matter, as long as the topology is preserved. Moreover, whenever you decide to make corrections, so your neural network outputs something, and there is another neural network that will make small corrections to that output, it needs to be essentially any correction needs to not care about what other corrections have done, right? So that's invariance is also very important. And not only that, it needs to be aligned with the way that a linear programming solver would try to make corrections, but in a much faster way. So this is a very complex architecture. I'm not going to go through it, but essentially all these symmetries are imposed into the neural network. So this architecture has all these symmetries. And by doing so, if you look at the state of the art at the time we published the paper, we see that if you have failures, if you have traffic anomalies, then the existing methods would have a very difficult time in correctly predicting where the traffic is supposed to go, because they were pre-trained on something and now things look different, right? But if you impose the symmetries, it's forcing the neural network to learn general rules that are transferable. And then if you have routing failures, etc., it's okay. So here at 1 means that the algorithm is optimal, right? And anything above 1, it means that it's much worse. So anything in practice, anything above 1.1 is really bad. And you can see that under failures, these existing methods are pretty bad. And then this method with all the symmetries, you can see that it's very close to optimal, even in cases in topologies that I had never seen, right? Many links have failed. And the thing is that the notion of alignment, like how well the algorithm is related to the actual solver that would solve this problem, is an important one, and we also can show that it's important to have this type of an alignment. I'm not going to describe what this means in detail, but just saying that that if you know something about the problem, it's important to add that to your neural architecture. Let me skip this part and let's talk a little bit about physics machine learning. And the point is, again, for this part, there is an important symmetry that needs to be at play here. So as I said, if you train, for instance, we have this pendulum and we train with small angles, and then we test with large angles, the existing methods will not be able to predict things well, because it doesn't look, the input doesn't look like what it has seen before. And so therefore the neural network embeddings will look very different, and the functions were not trained to deal with those differences, right? So, and you can see that not only in pendulum, say you want to have a Lotka-Volterra simple example, and again, techniques will fail because it's out of distribution for them, they get confused. So what we have done here then is essentially we have forced the symmetry, and the symmetry is related to causality. I don't have time to go into details. I'm happy to answer questions on this. Essentially what we are trying to do is we are trying to identify the causal structure between the different possible hypotheses for how this physics equation is supposed to work. And then there is what we have done is essentially a bi-level meta-learning objective, where first we decide which kind of functions are causally related to the output, and then we look for examples in the data that would violate that symmetry. So essentially, if we say that these possible functions here are not causally related to the output, we can ignore them, right? In the way that we are trying to model this differential equation. So it's essentially making the differential equation invariant to these possible functions. So the model then is looking for the most invariant possible function that you can find, and it's also looking for evidence in the data where a few consistent examples will say, actually, I think you are being too invariant here. There is something on these examples that tell me that you are missing one important function. And by putting this together, we can prove actually that under some conditions, this algorithm, which we call metaphysica, identifies a true causal structure if these basis functions are orthogonal. I can't describe that in more detail, but essentially it requires the causal problem to be identifiable from observational data. It's interesting. There are many details that I can explain at the question time. And one of the things that we are interested in doing with this is essentially kind of fixing these issues with physics simulations, right? So we're currently working on applying these ideas to 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 solve this issue with using neural networks for computational fluid dynamics. Um, and then, so what I will finish up then, I will say that zero-shot domain generalization requires new ways for neural networks to learn rules that generalize across domain without evidence in the data, right? Because a test domain you've never seen, so you don't have any evidence in your current data that what the test domain is like. So you have to be able to impose some sort of symmetry, some sort of constraint in your learning, so that when you learn, you end up learning more general rules. And with that, we should open for questions, if there are any questions. Thank you for having me.
Well, Bruno, thank you for such an informative talk. Now we're gonna see if we have any questions in the chat. We do. Pegue esse aqui mesmo. Samuel's question is: what are the main challenges and difficulties involved in the zero-shot learning when we are dealing specifically with the abstract images?
Sorry, say that again.
Peraí,
For image, for
what,
vision.
what are the main challenges and difficulties involved in the zero-shot learning when we are dealing specifically with abstract images?
Abstract images. Yeah.
Yes.
So you mean like you have an image that you never seen before, something very different, and then you have to predict what that is, right? Um, yeah. This is a difficult question. Like so my hypothesis is that if you don't know some kind of symmetry that should be imposed on your neural network, I find it very difficult that it will be able to learn rules that will transfer, right? Because the data really doesn't have anything. So you need to be able to tell it, look, out of all possible hypotheses you have, uh, there are things in the input that won't matter, right? So and if you think about how we learn, right? We learn in a scenario and we kind of abstract that away. Like we generally think, oh, it's not specific to this instance, right? This event happened and it's not specific to this instance, it's general. So there isn't a symmetry that we are assuming. And then when we go to a new domain, right, we try to map what are the entities, what are the relations on the example that we saw to that. So I feel that if you have some really different images, you must impose some kind of symmetry between in your neural network to be able to interpret those.
Okay. We do have another question. How can a model see an abstract image, for example, in landscape, and say clearly and in a great detail what they are seeing?
Sorry, say that again. I didn't understand.
Okay. How can a model see an abstract image, for example, in landscape? Sorry, I need to repeat. How can a model see an abstract image, for example, a landscape, and say clearly and in great detail what they are seeing?
Oh, like, but when you say abstract, you mean just regular like things, like in the
Yeah,
world?
like a landscape or
Yeah, well, the thing is that it was trained on, so when you are showing a landscape, right, you're showing a landscape on Earth, I'm assuming. And the visual model has been trained on a lot of landscapes
Yeah.
on Earth. And if you think about Mars, Arizona and Mars may not be that different, right?
Okay.
So it's not that it's really a domain transfer like it in that case. Like if you were to show something really different, like there are two floors, right? There is one floor here and one floor here, and the sky is in the middle. Uh, then the model would get confused, right? Because it's never seen
Mhm.
something like this. It could get confused. Although the convolutional neural networks, um, vision transformers last, they have this shifting variance, which is like they give the same neural representations no matter where the object is located. So if you have a ceiling on top and a ceiling at the bottom, the representations are still things that make sense to the model. So maybe that example is not a great example, but definitely, it's possible that some alien planet would not work because it would be out of domain.
Okay.
Also, one thing about vision out of domain, right? So Tesla is concerned about being out of domain. You see this example here, right, where they have to simulate people running on the street.
Mm-hmm.
Um, so this is out of domain for them. Like this is out of distribution at least. Um, so you need to do things sometimes like that.
Can I go to the next question,
Sure.
or do you want to add something? Okay. Um, what do you imagine the future will be with the improvements in the development of this technology on a large scale?
Yeah, that's a great question. Actually, I will say that specifically this work here, it when we started working on this, I thought this was impossible. There is no way this task is doable, right?
Mm-hmm.
The features are very different. They live in different space. They have nothing to do with each other. How is it possible that the neural network is going to learn on one and transfer to the other? It sounded like an impossible task, but there was a mathematical reason for why it could work. And I thought, well, because of math, let's do that. Let's try and be guided by math, not intuition, because intuition here goes out the window. And the reality is, it works extremely well. And I am honestly very surprised. And I'll tell you more. The fact that I'm so surprised by this is also tells me that someone was asking me if I can understand why it is able to transfer so well. And I said, and my answer really is that I don't think the human brain is capable of understanding it. Like we are reaching a point. It's not that it's a black box. It's not that. It's that it's learning something about the data that even if it explained to us, in even if it's absolutely correct and true, and it explained to us in the like a child, right, in greatest detail, our brain may not be able to understand it. It's because if you think about dependence tests, right, hypothesis testing, independence tests, we have been doing the same thing for 100 years, and we honestly kind of, if you really think about it, my view is that we haven't really come up with very different tests than what was designed originally, right, 100 years ago. So we have a really hard time understanding relationships and dependencies. And I feel that on this one, even if the neural network is able to perfectly explain, I don't think we won't understand. So I think there is a concept of transferability, that neural networks are able to do that are way better than we can possibly ever do. So there is I believe now that there is a good chance that the next generation of neural networks that have these properties will be so much smarter than us that we will not even understand how we can do things right.
Um, I will go to the next question, okay? Or do you want to add something to
Now go ahead.
this? Okay. Um, George's question is, could you explain the part of the casual DAGs in the beginning? The idea is to insert casual knowledge in the models for better generalization, but if we obtain the graph from data, aren't we in the same?
This one.
I believe so.
Okay. Yeah. So the thing is, um, right. So what's the relationship? What is common between sports and organizations? Right. Definitely, the jobs are not common. Right. Racing driver, you're not going to find in an organization. Um, Team principle is something that you're not going to find in organization. The actual people involved and the actual objects, entities involved, is not, you're not going to find here either, right?
Mhm.
So your model needs to understand that it cannot learn something based on these specific entities and relations. It can't, because it will see something different in test and it will get confused, right? It's never seen it. It doesn't know what field off is, because in sports there is no such relation, right? It doesn't know what coworker is, because in sports there are teammates, there are other things, right? The relations are described differently. So you need to tell the neural network, hey, you need to learn whatever you learn, your neural embeddings for this. They cannot pay attention to these details. Therefore, they must be invariant to this, to changes. Like it should not, changing race driver to some other arbitrary name should not matter at all, right? Um, and once you do that, it's a constraint, and it's a very strong constraint if you think about it. But actually, if you really think about it, graph neural networks also have very strong constraints. They say that the actual entities, their names, don't matter. A graph neural network will have that type of constraint also. So we are just adding another constraint to graph neural networks. And if that's the case, right, then you know that your neural network is incapable of paying attention to these details to make better predictions. So if they change, at least it's more robust, you see? And one thing that I would say, though, that it's again surprising to me, is that I thought, well, this is a very strong symmetry, right? This is a very strong assumption we are making. Uh, it's surprising that it works so well, right? And then I had someone asking me like, why is it that is it possible, right? Like, how can I learn in sports and test on healthcare? That doesn't make sense. Why should it work? And I think that the answer here is really that, if you really go think about these things, is that these are all things built by humans, right? These organizations, sports organizations, art, healthcare, we build these things, right? Like it's relationship between the different entities in healthcare systems. Humans build this thing, and it seems like we build the same thing over and over again. It's just with slightly different structures, like different names, but the thing itself is is built by humans. So it seems to be learning these patterns. And now, if you ask, well, okay, so what are the patterns then that it's learning? We don't really understand. You see, like I think we are getting to a point where if we impose these symmetries in the neural network, it will learn something, right? And what I find often is that I can't really understand. I'm not capable of really understanding what it's learning, but it's learning something right, because we see that when we ask to make predictions.
Next question is from Rodrigo. Rodrigo. He's a PhD in agriculture, and his question is, do you know any example applied to my study area? Any paper in agriculture?
Um, for domain transferability, not sure. If you email me, I can maybe find something. One thing that we did for with the work of Metaphysica actually started with us doing nitrate sensing on soil. We want to measure the amount of nitrate with a biodegradable sensor. And the problem was that whenever we changed the fields, the measurements were very different. So there was always a domain transferability across the different fields. And that's one of the reasons why we started the work of metaphysics. Is like, okay, so if we are doing physics guided machine learning, we want to be able to train on some fields at Purdue and then apply some other fields in minimally Illinois, right? But it wouldn't work well. And then we started thinking, okay, so how can we solve this? So that work. So we have actually a paper on the nitrate sensing part. But more generally, in agriculture, there are a lot of examples like that, or at least examples of tasks, right? Solutions. I don't think right now we have a solution for this problem of training on some domain and physics and testing on a different domain that's really super robust. Our method is way better, but it's still like, I think there's a lot to do on that.
Okay. Okay. We have another question from Mateo. How are these constraints enforced in the neural network?
Oh, so yeah, that's a great question. And the answer to that is through group theory. That's what we use. So you can, I have a web page that describes how these things work, and I can leave with the organizers. The website is invariances.org. So if you go to invariances.org, there's a tutorial there on how these invariances work, right? How the symmetries are imposed into neural networks. And if you like linear algebra and you like group theory, that's the website for you, because that essentially a lot of these symmetries are imposed through using group theory.
Okay. Can I go to the next question?
Sure, yeah.
Daniel question is, do you have any example in the material science? How would it be possible to use symmetry to identify and transfer the discovery of one causal structure from one material domain to another?
Oh, that's a great question. There has been some works on using symmetries to do transferability in material science. I can send you some papers. There is even like there are faculty here at Purdue that does that, and faculty in many other universities that work on this specific area. And in material science, it's very important to have this domain transferability.
Um, I believe we don't have any more questions.
I do have a question.
Um,
Um, Hello.
Okay, great. Thank you so much. I'd like to leave a shout out to my nephew who studies at USP, Lucas. Lucas, if you're hearing, hello. He's at the Polytechnic. He's doing computer engineering. Okay, thank you so much for your time. And if you folks do have questions, please let me know. I'll send the website to the organizers so they can post on YouTube and you can check it out.
Thank you so much for your presentation, Bruno. It was an excellent talk. Thank you so much. We are looking forward to see you again. Bye bye.
Excellent. Thank you for inviting me. Bye.